video we are going to see about the biomass yield. Typically we have seen some electron balance, element and balance, and valence calculations, degree of reduction calculation, and reciprocity quotient identification. All those things we have seen in the previous videos. However, one electron balance, two elemental balance, and one measured quantity are inadequate for the 5 unknown coefficients. So another experimental quantity is required. So during the cell growth, there is a general approximation. We always say a linear relationship between the amount of biomass produced and the amount of substrate consumed. So this relationship can be expressed quantitatively using the biomass yield, that is y of x is equal to mass of cells or gram of cells produced by gram of substrate consumed. A large number of factors which influences the biomass yield, including the medium composition, nature of the carbon nitrogen source, pH and temperature. So the biomass yield is greater in the aerobic conditions than in the anaerobic cultures. The choice of the electron acceptor, for example the oxygen or nitrate or sulfate, have also a significant effect on the biomass yield. So when the yield is constant throughout the growth, its experimentally determined value can be used to evaluate the stoichiometric coefficient. So when this can also be represented as instead of gram of cells produced by gram of substrate consumed, we can consider it as a molecular weight of the cells divided by molecular weight of the substrate. Here the molecular weight of the cells means the biomass formula weight plus any residual ash. Okay, please note it down. The molecular weight of the cells means the biomass formula weight plus residual ash. So before applying the measured values of y-axis in order to evaluate C, we must be sure that the experimental culture system is well represented by a stoichiometric equation. For example, we must be sure about the substrate is not used in any other types of reaction. One complication with the real culture is that some fraction of the substrate is consumed always, used for the maintenance activities like maintaining the membrane potential or internal pH or turnover of your cellular components and cell motility, etc. So these metabolic functions require substrate but do not necessarily produce cell biomass or carbon dioxide or water as described in our very first equation. So the maintenance requirements and the difference between the observed and true yields also we need to discuss, but not now. It will be in next chapters. For the time being, we will assume the available values for biomass yield reflect the consumption of substrate only as represented in our stoichiometric equation. Then coming to the product stoichiometry, in many fermentations, the extracellular products are formed during the growth in addition to the biomass production. When this occurs, the stoichiometric equation can be modified to reflect the product synthesis. So in our very first equation, we have seen some value for some equation for product also, where the product synthesis introduces one extra unknown stoichiometric equation coefficient to the equation. We have seen about A, B, C, D, E, right? So F will be involved in the case of product formation. So this is usually provided as another experimentally determined yield coefficient, that is product yield from substrate, Y of PS. So gram product produced by gram substrate consumed, or else you can tell this as molecular weight of the product by molecular weight of the substrate. So This does not hold if the product formation is not directly linked with growth. It cannot be applied for secondary metabolite production, as in the case of penicillin fermentation or the biotransformation which occurs in the steroids that involve only a very small number of enzymes in the cells. In these cases, independent reaction equations must be used to describe the growth and product synthesis. So here you can see the equations. Y of x is equal to cells by substrate, initial and final levels. So here you can find the equation eta into sigma s by sigma s gamma s by sigma b by gamma b. You all know the gamma s, gamma b are degree of reduction of substrate and degree of reduction of biomass. Eta is the energetic biomass yield. So sigma s is the atomic weight of the carbon divided by the molecular weight of substance. Here the atomic weight of the carbon divided by molecular weight of the biomass. In the similar way, here sigma s and sigma p will be calculated, and here eta is energetic biomass yield. Here the epsilon is energetic product yield. See in this page the same equation. Now I am going to explain what is the eta is about, because we know both the gamma values and sigma values we have seen. This eta is what we have seen in the electron balance reactions. In that oxygen demand calculation, we have seen one final equation. I have told you, like the fraction of available electrons for the conversion of transformation of substrate to oxygen, and as well as substrate to biomass, as well as substrate to product. We have seen, I have mentioned in the equation 6 in the electron balance video. So you go and see that equation Yc gamma b by gamma s, that is your eta, that is fraction of available electrons for the transformation from substrate to biomass. So that is your eta value. So in this y of x of s, I am substituting that eta value here. So here you can see, you can strike out the gamma b and gamma s. So finally you will be getting Yc gamma s Yc gamma s by gamma b. This is biomass yield. It is greater in the aerobic than the anaerobic culture. The value, if you try for some problems, you will come to know how it is coming greater for the aerobic and the anaerobic culture. So in this case, one more thing we need to see here, the C value. So the C is about the maximum possible yield. If they ask you to calculate maximum possible yield, please note it down. Here the C is defined as the fraction of available electrons in the substrate which transfer to the biomass. So in the absence of product formation, if all available electrons were used only for biomass synthesis, please note this point. If you are having the equation, do you remember your substrate plus your oxygen consumption, which gives the biomass plus product plus carbon dioxide, water and heat. So in the case of absence of product formation, all the available electrons will be transferred only for biomass synthesis. In this case, the Cb value will be unity. Cb value will be equal to 1. What is Cb? The available electrons in the substrate transferred to the biomass. So under this condition, there is no product formation. The maximum value of the stoichiometric coefficient C is, you have to calculate the degree of reduction of substrate divided by degree of reduction of your biomass. I forgot to note down in this page, so please note it down. Your Cmax is equal to degree of reduction of substrate divided by degree of reduction of biomass. into your gram carbon atoms for the particular substrate. So, therefore, if we don't know the stoichiometric growth, we can quickly calculate the upper limit for biomass yield from the molecular formula of the substrate and product. Normally, you know all the biomass formula is CH 1.8, oxygen 0.5 and nitrogen 0.2. So in that case, you can take your biomass value gamma B as 4.2. Please note it down, CH 1.8, O 0.5, N 0.2. In this case, the generalized biomass composition. In that case, your gamma B, that is degree of reduction of your biomass, is 4.2. Okay. So now the maximum biomass yield can be expressed as the number of C atoms in the biomass per gram atom of the substrate consumed. I will be explaining this concept in detail in the problem we are going to solve in the next video.